let's move on to the next section, which is aromatics. So with aromatics, the first portion is going to be electrophilic aromatic substitution. And so just remember to review that with electrophilic aromatic substitution, your ring is acting as a nucleophile, okay? And so let's start off with nitration. So with nitration, you have HNO3 and H2SO4. And so we're going to add the NO2, or we're going to add an NO2 group to our ring, okay? And so I highly advise, sorry, one second. Okay. We're going to add an NO2 to our ring, okay? And there are two ways you can add, okay? I recommend that you review my other video, which is that should be about resonance and adding groups to the ortho, meta, and para positions of the ring. Essentially, since this is an EDG, we're going to add it to the para position and the ortho position. And this is our major product. This would be our minor product. All right. Next, we have sulfonation. So sulfonation, we're going to add an SO3H group. Okay, and just a reminder that this is reversible with acid and water. Okay. So next in our chain of aromatic additions, we're going to halogenate, okay? And so with halogenation, we're essentially adding your halide group, okay? But remember that in this case, we have an electron withdrawing group, and so our major product is going to be added to your meta position. Okay, so in this case, we took Br2 and FeBr3, which is your Lewis acid catalyst, and we're going to add bromine onto the ring. Next, we have Friedel-Crafts alkylation, okay? And so with Friedel-Crafts alkylation, we are going to add an alkyl group to our ring, okay? And so there are a lot of different criteria that are special for alkylation, and the next one, acylation. So I really recommend that you go through your notes because we won't be able to cover it in this video. Okay, and then next we have acylation. So we're going to take our acyl group with a carbonyl on it, okay, and we're going to add that carbonyl group to the ring. Okay, next we have benzylic oxidation. Okay, and so in benzylic oxidation, we're going to take KMNO4, H2O, and KOH, or you can do the same reagents as Jones oxidation, which is, if you remember, K2CR2O7. Okay, and so under these conditions, we're going to take the benzylic CH3 or the benzylic carbon group, and we're going to replace it with carboxylic acid. Okay, and again, there are other criteria for this, but go ahead and review that from your notes. Okay, so now we're going into nucleophilic aromatic substitution. So this is different from electrophilic aromatic substitution, okay? And this is because we're going to, in this case, our ring is acting as the electrophile, excuse me, sorry. And so we're going to take, or notice, first of all, that your starting product has a leaving group, okay? And so this is the first indication that this is nucleophilic aromatic substitution, because remember, in order for a nucleophile to attack, you need a leaving group. And so we can take any nucleophile, all right, and then we're going to replace our bromine with your nuke. Okay. Next, we have the benzyne intermediate nucleophilic aromatic substitution. And so this is when you don't have any electron withdrawing groups on your ring and you only have a leaving group. And so in this case, we're going to take Na, NH2, and NH3, or so ammonia as the solvent, and we're going to replace that leaving group with NH2. Okay. And so in general, just to reiterate, we do the benzene intermediate SNAR whenever we don't have electron withdrawing groups on our ring, or we have really poor electron withdrawing groups on our ring. Okay. Next, we have Birch reduction. Okay, so in the case of Birch reduction, first I'm just going to replace those OCH3s with R groups, okay? And so in this case, the main thing that we're doing is we're going to add hydrogens such that they're ortho and meta to both of the R groups, okay? And so in this case, this is meta, okay? And in this case, this is ortho, okay? So we add those hydrogens, and then we're going to create two double bonds that are parallel to those hydrogens that we just added, okay? And so in this case, we're going, just note that we're going from an aromatic compound to a non-aromatic compound. All right. Now, we have the biggest section, but this is the last section we have, which is carbonyls. So with carbonyls, first we have sodium borohydride reduction, okay? And so in this case, we can reduce, so add hydrogens to a carbonyl, and in this case, aldehydes or ketones. And we're going to turn the aldehyde into an alcohol, okay? The same thing can be applied to lithium aluminum hydride reduction. And so in the case of aldehydes and ketones, we're going to get the alcohol product. But also note that lithium aluminum hydride can also work on carboxylic acids and esters. And so we've already gone over these types of reductions, so I recommend backtracking to the carboxylic acid section or the ester section if you're not sure what product is formed. Next, we have general cyanohydrin formation. And so in this case, we're taking our carbonyl, and that the cyano group is going to attack. So first of all, we're going to protonate because it's an acid, and we protonate that carbonyl to get an alcohol, and then we add our cyano group, so our nitrile. Next, we have acetal formation. And so with acetal formation, we're essentially adding your alcohol group to this carbonyl. And so what that looks like, let's first draw our benzene ring. Okay. And so in this case, we're going to add the alcohol group, and that carbonyl becomes an alcohol. And so this is the halfway point. This is our hemiacetal. But in order to form the full acetal, we need a second equivalent of your alcohol to replace that last alcohol group right here. And so we're going to add the second alcohol, and this is our acetal. We also have the ketal. The ketal this is essentially the same reaction as an acetal, except we're doing this on a ketone. So in this case, our alcohol is a phenol because of the phenyl group. And so in this reaction, remember our carbonyl becomes the alcohol in what is known as the hemiacetal or hemiketal. Okay, this is the halfway point. And then we're going to add the phenol onto our molecule. Upon adding a second phenol, we're going to replace the alcohol in the molecule with another phenol. Okay, and so this is ketal formation. Next, we have a diol protecting group. Okay, and so diol protecting groups, essentially what we're doing is we're going to protect an aldehyde or a ketone with a diol. And so we're going to take the carbon that has the carbonyl on it, and then we're going to essentially add that diol onto our molecule, like so, okay? And so essentially this is the same thing as a ketal formation, except this is intramolecular. Both equivalents of your alcohol are coming from the diol. Okay, and in all of these reactions, we can reverse them and get our carbonyl back by using HCl and H2O. Okay. Last few reactions, we have imine formation. So with imine formation, the main difference is we're taking a primary amine and reacting it with a carbonyl. And so in this case, we're going to take we're going to replace that carbonyl with a double bonded N, and then we're going to add the carbon group. Sorry. Like so. And then finish off that molecule. Okay. So this is imine formation. With enamine formation, this is when you have a secondary amine. We're going to first draw out carbon structure. And in this case, we're going to add our nitrogen like so, but instead of forming a double bond like in the imine, in the enamine, we're going to form a double bond next to the nitrogen, not on the nitrogen, but next to it, okay? And so again, please review the mechanism for this in your notes. Okay, for Strecker synthesis, this is to create an amino acid, and so amino acids have a amine group and a carboxylic group, okay? And so with Strecker synthesis, we're going to take our carbonyl, we're going to use an ammonia nucleophile to attack that carbonyl and create this species right here, okay? And then from there, we're going to use HCN. And in doing this, we're going to create this molecule right here with the amine and the cyano group on the same carbon. From here, we're going to do a nitrile hydrolysis, okay? And we turn that CN group into a carboxylic acid, like so. And so for our last two reactions, we have Wolff-Kishner reduction and Clemmensen reduction. These do the exactly same thing, or the main difference is just the reagents. So with Wolff-Kishner reduction and Clemmensen reduction, we're going to add 2 hydrogens to our aldehyde, or our ketone in this case, and reduce it by adding 2 hydrogens. Like so. Okay. And so that's all of the reactions that we've pretty much gone through for this whole class. And so, again, I really recommend that you look into these reactions more in depth and look at your notes, look at the certain specificities, the stereospecificity, stereoselectivity, all of those fine details about these reactions. But the main point of this video was to essentially take all the reactions we know of and organize them into neat little categories that will help you as you study and hopefully maybe when you're taking this exam, okay? But anyways, that should be all for this video.